Hi, and great to see you here on my YouTube channel. In this video, I'll talk about the pitfalls you might run into when building native images with Quarkus. These videos serve as a valuable supplement to my comprehensive Udemy course where I systematically cover the fundamentals and advanced topics through a hands-on example application. If you find this content helpful and want to deepen your understanding of Quarkus, I encourage you to check out my Udemy course. You'll discover additional resources, practical exercises, and insights designed to help you build a solid foundation in Quarkus. The link is in the description below. But now let's get started. The use of Quarkus extensions ensures that the application can be compiled natively and the integrated framework or library works as it should at runtime. Nevertheless, you may encounter problems at runtime that Quarkus cannot solve for you, as the causes lie in your own implementation. I would like to introduce you to a few pitfalls here and show you how you can avoid them. To do this, I created a new Quarkus app from scratch, implemented various REST resources, and then compiled the application natively. I run the application locally in a Docker container under port 12345. Let's start with a reflection resource. You can run into problems related to reflection relatively quickly. Quarkus uses GraalVM and native image technology to create a native image. The call tree of all calls in your application is analyzed. All classes, methods, or fields that are not part of this call tree are not compiled into the native image. I have implemented 3 endpoints in this resource, some of which work in the native image and some of which do not. In the first example here, in the reflection register method, a JSON string is received, deserialized into an object of the foo class via JSON object mapper, and then returned as a response body. The second endpoint, reflection not registered, works in exactly the same way, but uses a different class bar as the deserialization target, and the last method call creates an object foo bar, which is returned in the response body directly. I have prepared corresponding example requests for all endpoints. Without looking at the classes foo, bar, or foo bar, let's see how the endpoints behave. In the first example, I sent this JSON as a payload and received this response. So the endpoint was able to process the request. The second request here to the second endpoint with target class bar runs into an error, and the first request, in whose context the class foobar is instantiated directly, also runs into a runtime error. A look at the log file in the container reveals that Quarkus has problems initiating the foobar class, for example. It does not appear to be part of the native image, so why does the first endpoint based on reflection work? The reason lies in the implementation of the foo class. The implementation is irrelevant. The only important thing here is that it is annotated with register for reflection. When Quarkus analyzes the reflection register method, it sees that the method returns an object from response class. Therefore, response becomes part of the native image, but not automatically foo. Foo is used via reflection, so you have to explicitly tell Quarkus that you want to include foo in the native image. This is exactly what the register for reflection annotation does for you. The reason why the second endpoint does not work, although it is implemented identically with the exception of the bar class, lies in the bar class itself. The aforementioned annotation is missing here, which is why this class is not part of the native image. But why does the third endpoint does not work? This is not based on reflection, and we still run into errors. Foobar is also structurally identical to foo and bar. The reason here is in the use of the response class as a return type. Response can hold any objects in the response body. Foobar, from my example, does not play a role here. Although a new instance is created within the call method, it is not returned directly as a return type, and nothing else is done with it that Quarkus causes to include it in the native image. In this case, the class does not become part of the native image. However, you can also use register for reflection to change this. So in addition to reflection, you may have problems with static resources in your application. Here's another implementation of a REST resource with two endpoints. The first one loads a static resource foo.json in the folder foo and returns the path to that resource. The second endpoint works in exactly the same way but returns the path to the bar.json file in the foo folder. The first endpoint works, while the second endpoint runs into problems. A look at the log in the container reveals that bar.json is apparently not available. The thing is that foo.json and bar.json are stored in source main resources. Resources from this folder are included in a jar during a Maven build, but are not part of the native image. This only applies to resources located in meta-inf/resources, which are then available as static web resources. You should therefore only place resources there that you also want to host statically. For all other resources, you must register them for inclusion in the native image. This is done via the property quarkus.native.resources.includes, which is a comma-separated list of all file paths. Glob expressions are also allowed here, and you can see that I have only registered foo.json, but not bar.json. And finally, you may have problems with static members of Java classes. So let's take a look at this REST resource. There are three endpoints here. All of them provide dummy system information. The structure here is again irrelevant. The only important thing is that I pass in the value application started here in the first endpoint, which is a static long in this class and contains the current timestamp in milliseconds. The second endpoint works in a very similar way. Here, however, the values come from a different class called application started, but is also implemented statically here. The third endpoint also works in the exact same way, but here the information about the application start comes from a CDI singleton and is not implemented statically. Let's take a look at how the endpoints behave here, and I would like to look in particular at the timestamp returned. I will first note the timestamp returned for all three endpoints. The value is initially irrelevant. The second request is now exciting after I have restarted the container once. Let's do so quickly. If I now repeat the first request and compare the timestamp with the one from the first request, I notice that it's exactly the same. Should it be different? After all, I've just restarted the application. The reason lies in the fact that Quarkus fixes static members of a class when the native image is created. This is at build time. Since the first implementation uses a static field from my REST resource, this no longer changes until I create a new image. The second request does not have this problem. Also here too, the value comes from a static field of the application started class. I have configured this class in the properties so that it is loaded at runtime. This is possible via the property quarkus.native.additionalBuildArgs. Here you can use the initialize at runtime switch to specify a comma-separated list of packages or classes that are to be loaded first at runtime. Glob expressions are also allowed here. Quarkus will take this into account when calling the native image command. The implementation with a CDI singleton always provides different timestamps, as a timestamp is not modeled as a static field, but as a class member. Further information and tips on building native images with Quarkus can be found in the linked guide.